Hello again, this is Jennifer Martinez, and in this video we're going to look at the orthogonal decomposition theorem. So let's let W be a subspace of Rn. Then each y in Rn can be written uniquely in the form of y plus y hat plus some z, where y hat is in W and z is in W complement. In fact, if a set of vectors u1 through up is any orthogonal basis of W, then y hat is going to be written as a linear combination of u1 through up, where each constant, like is in the last section, is a projection onto the line. This would be a projection onto u1. The next one would be a projection onto u2 and so forth. Y hat is called the orthogonal projection of y onto the subspace W, instead of like the last section onto an actual line, and is often written as the projection of W instead of L here of that vector y. When W is a one-dimensional subspace, the formula z minus the vector y minus y hat can be thought of in this way. So here is the green is the subspace W, and here is the vector y in orange, and y hat is considered the projection of y onto W. So there it is right there. Right here in green. So if you subtract y minus y hat, you end up with the dotted line right here, or this z. They have it here from z, y minus y hat. The orthogonal projection of y onto W is what this is. So here's the proof. Let's look at the set u1 through up and let it be an orthogonal basis for a subspace W, or for the subspace W of Rn. And let's define y prime as in the equation up here in the theorem number 2. We know that y hat is in the subspace W. It makes sense because y hat is a linear combination of u1 through up. So it's a linear combination of the basis. So we're going to let z equal y minus y hat. And since u1 is orthogonal to u2 all the way through up, it follows that if we look at z dotted with u1, which is y minus y hat dotted with u1, which is y dotted with u1 minus y hat dotted with u1, and let's write down what y hat is. Since y hat from 2 is this whole big equation up here in the blue, we can plug that into y hat here, and each one of these is 0 except for that very first term. So that's what all these zeros are for. And so you end up getting y dotted with u1 since these cancel. So it does equal 0. And then you can do the same thing for z dotted with u2. So we're going to see that z is orthogonal to each uj in the basis for W. Hence, z is an orthogonal to every vector in W. That is, z is in the U complement. So that shows this part. So let W be of Rn. Y is in Rn can be written in this form, where y hat is in W. We saw that. We let y hat be in W, and z be in the W complement. So now we would just want to show that it's unique. To show that this composition is unique, we suppose that there's another one, and then they show that the left side is equal to the right. So you could check that out. So we're going to use this theorem for example 2. So what does example 2 say? Example 2 is let u1 be the vector 2, 5, negative 1, and u2 be the vector negative 2, 1, 1, and a vector y is 1, 2, 3. First, observe that U1, U2 is an orthogonal basis for W, where W is the span of U1 and U2. We do see that these are independent. So it is a orthogonal basis, because if we look at U1 dotted with U2, we do get the 2 times negative 2 plus 5 times 1 plus negative 1 times 1, which is indeed negative 4 plus 5 minus 1, which is 0. And since there's only 2 vectors, they are independent, so it is a basis. We do have that U1 and U2 is an orthogonal basis for the span of U1 and U2. So let's let Y be the sum of a vector in W and a vector in the orthogonal to W in W complement. By looking at the orthogonal projection of Y onto W, Y hat. And by the theorem, Y hat, which by the way is again the projection W of Y, is equal to the linear combination of U1 and U2, where the constant of the U1 is Y dotted with U1 over U1 dotted with U1, and the constant of the U2 is Y dotted with U2 over U2 dotted with U2. So let's list these. Y dotted with U1. That is equal to 2 times 1, which is 2, plus 5 times 2, which is 10, plus negative 1 times the 3, which is negative 3, which is 9. U1 dotted with itself is 4 plus 25 plus 1, so that would be 30. And then Y dotted with U2 is going to be the Y with the U2, so that's going to be negative 2 plus 2 plus 3, so that will be 3. And then finally U2 dotted with U2 is going to be just 4 plus 1 plus 1, which is 6. So here we have Y hat would be, we have 9 over 30 times U1 plus 3 over 6 times U2. Those are the constants I'm going to use. We could reduce that to 3 goes in both of those, so that would be 3/10 of U1 plus 1/2 of U2. So that is my Y hat. We could also actually just figure out the vector of Y hat because we know what U1 and U2, oops, that's not U2, U1 and U2 is. So this would be equal to 3/10 times 2, 5, negative 1, plus 1/2 U2, which is negative 2, 1, and 1. So that would equal 6/10, 15/10, negative 3/10, plus negative 1, 1/2, and 1/2. And getting an LCD of all 10, making this negative 10 over 10, 5 over 10, and 5 over 10, we can add those and then reduce. So here is Y hat, negative 2/5, 2 and 1/5. And we know that Y hat is in W because we wrote it that way. Y hat is a linear combination of U1 and U2, and W is the span of U1 and U2. So therefore, Y hat is in W. And from the theorem, going back to the theorem, we see that if Y hat is in W and y hat is written this way, z being y minus y hat is going to be in y complement. So let's go ahead and do that. So z again is equal to y minus y hat is in y complement. That's what we proved before. So what is y minus y complement? Or sorry, y minus y hat. Y was given as 1, 2, 3. Y hat we just found, -2/5, 2 and 1/5, and that would be the z. So making the first and last term common denominators of 5 and adding the opposite, we have that z is going to be 7/5, 0, and 14/5. The example asks us to write y as a sum of a vector in W. So y hat we know is in W, and a vector in the orthogonal to W, which would be y complement, so that would be z. So y can be written in terms of y hat and z. Y hat being -2/5, 2 and 1/5, and z being 7/5, 0 and 14/5. And if you remember, y was 1, 2, 3 from above. There is y right there. So we just did it. We wrote y as the sum of a vector in W and a vector orthogonal to W. And you can see that this vector is, if you add these together, you do get 1, 2, and 3. And this one we know is in W, and this one we showed, which was in W complement. So that concludes example 2. So our last theorem that we're going to look at is called the best approximation theorem. And it turns out that this y hat that we found above, the y hat that we found using that decomposition theorem, is going to be the closest point in W to y. So let's read what this says. Let W be a subspace of Rn and y be any vector in Rn. So y, here's the 0. So y is that black line, that vector right there. That is Ry. And let y hat be the orthogonal projection. So there it is in blue there, the orthogonal projection. Let's make that vector blue. Of y onto W. Then y hat is the closest point in W to y, in the sense that if you look at the distance of y minus y hat, which is the dotted line, or the blue line here, this vector here, this is the distance z right there. This we'll call that the same thing of z, just to be simplified. That is always going to be smaller to the distance of y minus v for all v in W that is distinct from y hat. So let's choose a vector that's not y hat. Let's call this v. And v goes from 0 all the way to there. That's the vector. And we want to look at the distance of y minus v. Well, y minus v can be written as y minus y hat plus y hat minus v. And by the decomposition theorem, we know that y minus y hat is in W complement. Therefore, y minus v must be in W. They're orthogonal to each other. So we know from the first section that we have a Pythagorean theorem relationship. So let's look at that. I'm first going to erase my vector v there so I do not get confused, but I still have that dot where v is. We know that this vector is y minus y hat. So this vector is y hat minus v. So the hypotenuse, which is always larger than the leg, is y minus v.